Okay, well, welcome to the second talk today on our first day of the season. Today, for this talk, we have Chris Grossack, who will be talking about where are the open sets, comparing HoTT with classical topology. Please go ahead.
All right, fantastic. Thank you for the introduction, and obviously thank you to the organizers. It's a lot of fun to be here. So this talk is going to be about why theorems in homotopy type theory are still interesting to classical topologists, because of course we have some synthetic theory of homotopy theory. It's not at all obvious that if we prove that the fundamental group of the circle is the integers, that is true for the circle as is typically defined, even up to homotopy. So some disclaimers. This is only a 30-minute talk, so I'm going to necessarily be somewhat vague and somewhat fast-paced, so I'm sorry about that. But thankfully, anytime I'm waving my hands particularly vigorously, I'll have included sources that are more comprehensive and more detailed references. So what's the plan today? Well, as I said, HoTT is synthetic homotopy theory. So how do we know that our theorems are true in classical topology? Well, homotopy type theory is a logic. So what we were really asking for is some good semantics that let us interpret this logic in classical homotopy theory. This is a question that I had when I was first learning homotopy type theory, and it took me a long time to get a really coherent answer. And in part, that's because it's a difficult question, but in part, it's because it's annoying to write down. And thankfully, there have been a lot of really great resources recently for learning about this. And so I'm happy to help contribute to that. So the plan is going to be to start with homotopy type theory. And then we're going to have semantics that interpret the logic of homotopy type theory in the world of simplicial sets. And depending how fancy you feel, that's either going to be model category theoretic or infinity category theoretic. We'll be sticking with the language of model categories today because they're slightly quicker to introduce. And then we're going to pass along equivalence from the category of simplicial sets to the category of topological spaces. And that's going to give us, when you compose these arrows, some way of interpreting homotopy type theory in the category of topological spaces up to homotopy. So yeah, the equivalence is going to tell us that any category theoretic property of simplicial sets is also true of topological spaces up to homotopy. And I see there's a question for agnostic. But through our semantics, HoTT is also going to tell us, so our semantics will tell us true things about simplicial sets, which we then transfer along this equivalence in order to get true things about topological spaces. So let's go ahead and get started. So section 1 is going to be on model categories. This is far and away the longest section, so feel free to interrupt me whenever. And again, I'm going to be somewhat vague about the entire notion. So first of all, let's remember what the classical notion of homotopy is. If I have two continuous maps from spaces x to y, we say they're homotopic if there's some slightly bigger function from x across the interval to y, so that on the 0 side, I'm doing f, and on the 1 side, I'm doing g. And so you should view this as for every point x, I'm getting a path from f of x to g of x, and this is continuous both in x and the parameter. Or if you like, this is directly giving me a path between f and g. Such an H is called a homotopy from F to G, and we usually write that with this little twiddle. So we say that X and Y are homotopy equivalent, again, classically, if we have maps F from X to Y, G from Y to X, which maybe they're not inverses on the nose, but they're inverses up to homotopy. So instead of F compose G being equal to the identity on Y, we merely ask that it be homotopic to the identity on Y. And if you're familiar with categories, this is entirely analogous to the notion of equivalence of categories instead of isomorphism of categories. We're asking that we only get equality up to a 2-cell, so something like a natural transformation, so a homotopy here. And again, this looks like some kind of isomorphism, but, and it turns out to be a very, very useful thing to talk about spaces up to homotopy. For instance, the fundamental group is only defined up to homotopy, homology groups, for instance. So it would be nice if we could turn this notion of homotopy equivalence into some notion of equality or isomorphism in a category, so that somehow it's more hygienic that our invariance would be related to the actual notion of isomorphism or equivalence that we're using. So the plan is going to be to simply force this to be the case. So these look like an isomorphism. Well, let's just make them isomorphisms. So definition, we're going to say that W is the class of weak homotopy equivalences. Again, this is one of the things I'm going to gloss over. If you're not familiar what the difference between a homotopy and a weak homotopy equivalence is, don't worry about it. You can read about this in basically any book. But okay, the idea is that we're going to require that F induce isomorphisms on every homotopy group, whatever that means. And then we're going to define top of W inverse, what this notation is sort of stolen from localization of rings, is going to be the category we get by freely adding inverses for every weak equivalence. So we're just forcing every weak equivalence to have an inverse. That is, we're forcing every weak equivalence to become an isomorphism. So we have good news and we have bad news after doing this. The good news is that weak homotopy equivalence is now isomorphism, which is like exactly what we wanted. So this lets us do category theory more directly. This turns out to be a very useful thing to do. The bad news is that this category sucks, to use the technical definition. Basically, there's no limits or co-limits at all. There's a way of getting around this with these things called homotopy limits and co-limits, which is one of the things that model categories will help us do, but I won't talk about them in this talk. But more importantly than not having limits or co-limits, the arrows are like almost impossible to understand. So arrows in one of these localized categories in general corresponds to zigzags of arbitrary length of arrows in top. And this is just like really, I would say, impossible to truly get your head around. But there's good news again, because we don't need to work with these arrows directly. There's a notion of a model structure that we can put on top that will actually let us compute with this homotopy category top of W inverse. And yeah, so we can compute with spaces up to homotopy by using this model structure. The bad news again is I'm not going to tell you what a model structure is. So these are the downsides of working in a 30-minute talk. I'll give you some brief idea, but I'll point you to better references on model category theory if you want to like actually learn the definition. So here, for instance, is one, Homotopy Theories and Model Categories by Dwyer and Smolinski, a very, very famous reference, and with good reason. So briefly, the idea is that we're going to choose fibrations and co-fibrations in addition to the weak equivalences in our category, and they should satisfy certain axioms telling us that they behave nicely with the weak equivalences, and most importantly, fibrations and co-fibrations should lift against each other. So if you have a commutative square where the left side is a co-fibration, the right side is a fibration, and one of the two of them is a weak equivalence, then we're going to be able to fill a diagonal in a way that's going to come back later on in this talk. I'll have a picture that I can point you to, because this is sort of the reason that path induction works in a certain sense. So why should we care about one of these model categories? Well, it lets us compute in top up to homotopy by making computations in top, as long as we restrict attention to the objects that are both fibrant and co-fibrant. And so by doing this, if you've heard these words like fibrant replacement, that's sort of what's going on, is every object is weakly equivalent to an object which is both fibrant and co-fibrant. I see there's a question, I'll get to it in a second. So every object is weakly equivalent to one which is bifibrant or fibrant and co-fibrant. And so since now weak equivalences become isomorphisms, that's telling me every object is actually isomorphic to one which is super nice. And so by restricting attention to objects which are nice, we can actually do computations in this homotopy category. Oh, yes, perfect. Thank you for linking the reference paper. Fantastic. And again, see Dwyer and Smolinski for more details. Okay, but this is great as far as like working with classical topology works, but at some point we have to introduce simplicial sets. And so what does this have to do with simplicial sets? And like more importantly, what is a simplicial set? So the idea behind simplicial sets is a combinatorial model for topological spaces. And this is really nice for lots of reasons, but the idea is going to be to glue together. We have 0-dimensional objects, which are called points. We have 1-dimensional objects, which are arcs between those points, 2-dimensional objects, which are triangles between 3 arcs, 3-dimensional objects, which are tetrahedra filling in for triangles that you put into a tetrahedra, and so on. And so if you're trying to talk about these in general dimension, eventually we run out of names. So we call these 0 cells, 1 cells, 2 cells, 3 cells, or 0 simplices, 1 simplices, and so on. So here's an example of a very small simplicial set, or I guess it's geometricalization. So we have some set of 0 cells. So we have V1, V2, V3, V4 are our 0 cells. We have some 1 cells, so we have E1 and E2. There's nothing stopping you from gluing something together multiple times. I should have drawn a self loop as well. There's also nothing stopping you from having sort of degenerate things where you glue something together to itself. So we have these 1 cells drawn in purple. We have a 2 cell F drawn in orange. And if my artistic abilities were better, I would have drawn a 3 cell, but I didn't trust myself to do that. And we also have these face maps, which tell me basically what the boundaries of my edges are, or what the boundaries of my 2 cells are. And you should think about this in an oriented way, but I didn't feel like messing around with an orientation. I would probably get it wrong. So I'm going to guess and just orient things in order, increasing order of the vertices. So the edges, so E1 is connected to V2 and V1, right? So the face maps are telling me what's glued together. Or if I look at the 3 degeneracy maps of F, it's telling me that the boundary of F is I've done something, is E3, E4, and E5. Incredible. So, and of course you could do this for progressively higher things. And you see that we've described a topological space. So this is, I guess, homotopy equivalent to the circle, for instance. And we've described it using only finite amount of data, which is like awesome as far as like getting Agda to understand it, for instance. In general, we package this information into a diagram. We have our 0 cells x0, we have our 1 cells x1, and we have 2 maps, which you should think of as being the 2 endpoints of my arc from x1 to x0. We have 2 cells x2, and of course my 3, if you give me a triangle, I should tell you what its 3 edges are. So x2 to x1. I have 4 sides of the tetrahedron, and so on. And then also, like, there's these other arrows going in the other direction called the degeneracy maps. And again, I'm not going to tell you about those, but don't worry about it. This is conveniently realized as a functor into sets. Oh, and I will tell you of a reference if you do want to worry about it in a moment. But this is conveniently realized as a functor into sets. And we call this functor category S set for the category of simplicial sets. So our objects are going to be functors of this form into sets, and our arrows are going to be natural transformations between these things. For informations, you can see Friedman's elementary introduction to the category, elementary illustrated introduction to simplicial sets. There we go. Or you can see Singh has, I believe, a master's thesis, a survey of simplicial sets, which is also quite good and quite short. And both of these are really good references as far as understanding what simplicial sets are and why you might care. Okay, but now again, why are we talking about simplicial sets? It turns out there's a model structure on S set as well. And this is going to come back later on in the talk. The fibrant objects are called Kahn complexes. So if you've heard about, and every object is cofibrant. So if you've heard about these guys called Kahn complexes, this is one of the reasons to care, is when we're doing homotopy type theory, we're going to interpret our types as Kahn complexes. Okay. So moreover, we have translation functors. We have this guy called geometric realization, which takes a simplicial set and spits out a topological space. And the idea behind geometric realization is sort of the most obvious thing you can do. I gave you sort of a set of instructions for how to glue a bunch of simplices together. Well, okay, actually do the gluing. Like we have topological notions of simplices, and just do the gluing that the instructions told you to do, and you'll get some topological space. We also have this functor in the other direction called sing for singular chains. And what does this do? Well, if you give me a topological space, I'm supposed to give you some simplicial set. And I do this in simultaneously the dumbest but the most canonical way. My n-dimensional simplices inside of my topological space X are just going to be all continuous functions from the topological n simplex into my space X. You might recognize this from singular homology or cohomology if you've taken a class in more traditional algebraic topology. And when you do this, there are going to be obvious degeneracy. There's going to be obvious face and degeneracy maps that come from those of the topological simplices. Please move. Thank you. So it turns out these are adjoints. Geometric realization is left adjoint to the singular chain functor. And moreover, these play nicely with the model structures on simplicial set and top. Now, what do I mean by they play nicely? I mean theorem 1. These two functors induce new functors called the derived functors, so L of geometric realization and R of Sing, which take us from the homotopy category of simplicial sets with weak equivalences inverted to topological spaces with weak equivalences inverted, and going the other direction. So somehow these play nicely enough with the model structure that they actually descend to functors on the homotopy categories. And moreover, these functors form an adjoint equivalence between these two categories, which is fantastic, right? So this is called equivalent equivalence if you're looking for something to Google. And this is also discussed in, for instance, that paper Dwyer and Smolinski. Yes, this is discussed in more detail in the previous sources. And the punchline is we now have an equivalence of categories between the homotopy category of top and the homotopy category of S sets. So any question we have about topological spaces up to homotopy, as long as it's expressible in the language of category theory, which is one of the reasons people get so geeky about trying to say everything possible in the language of category theory, because it means that as soon as you have a question, if you know it can be expressed in that way, then you can transfer it along equivalences. And so any question we have within reason can be answered by just taking singular chains of all the spaces involved and then answering that question in simplicial sets. There's another question. Thank you. Another link to the paper. That's awesome. I appreciate it. Yeah, so that's the whole point, is now we can work with simplicial sets instead. And simplicial sets are nice combinatorial objects. So this is great news. In a very concrete sense, this is great news because simplicial sets are combinatorial. So it's much easier to tell a computer how to work with simplicial sets. So for instance, Sage Math, which is a fantastic package for doing mathematics on a computer, it basically exclusively works with simplicial sets, and it can compute homologies, cohomologies, fundamental groups, and so on for you, which is fantastic. Also, this is basically, in some moral sense, what's going on when we describe topological spaces in Agda. But also, so less concretely, but sort of also usefully, this category is a topos. It's a pre-sheaf category into sets. And this gives us access to a lot of heavy-duty category theoretic machinery, which will help us solve our problems sort of in a theoretical sense. And indeed, speaking of heavy-duty category theoretic machinery, what does all of this have to do with homotopy type theory? This is maybe a good place to stop and see if there's any questions. We're going to check in. Now we've talked about the model category theoretic stuff relating simplicial sets to the classical topological spaces. And in section 2, we're going to move on to discussing semantics of homotopy type theory. So if there's questions about things, now might be a good time to see what people have to ask. This section is much shorter as well. I'll wait like 30 seconds. Okay, that was a very short 30 seconds, but if a question comes up, it'll show up in chat. So what does all this have to do with homotopy type theory? Lots, obviously, but be warned, this is not for the faint of heart. We're going to move on. I'm going to gloss over a lot of things, but we have lots of references which have come out fairly recently for really describing in really good detail what's actually going on here if you want to get into the nitty-gritty details. So Emily Reel has this fantastic set of talks on the infinity topo semantics of HoTT. There's 3 lectures all on YouTube. Lectures 1 and 2 are probably the most useful for being analogous to filling in details for what I'm talking about here. There's also a set of lecture notes for the same series, which is fantastic. And then we have this other paper of Kopolkin and Lumsdain, which is, sorry, my thing is in the way, the simplicial model of univalent foundations, and that's after Voevodsky. So that's another fantastic paper, which will which does a fantastic job very concretely explaining what's happening here. Emily's talks are sort of with an eye towards the eventual semantics in any infinity topos, so it's naturally a little bit more abstract, whereas this paper does a much better job. Well, that is a different goal, but everything is very concrete. Like you really feel like you can compute with the semantics after reading this paper, or at least I did. Okay, and there's more links in chat. Thank you so much, people filling those in. Okay, so morally, what are we doing here? Well, types in homotopy type theory should get interpreted as Kahn complexes. That's what I was saying earlier. And constructions on types get reinterpreted as categorical constructions on these Kahn complexes. So let's see an example. Dependent types. So if I have X in type A, I have a family B of X, get modeled as fibrations. So I have some con complex B sitting over some con complex A. And my logician is showing I'm going to use these Scott brackets in order to denote the semantics of whatever syntax we're talking about. So if I have some syntactic object in homotopy type theory, when I wrap it in Scott brackets, that means I'm now talking about some honest to goodness thing built out of con complexes. That's a real simplicial set we can get our hands on. So sigma and pi types are given by adjunctions. Again, this is moral, are given by adjunctions from a certain projection map from a direct product. And so we have some base change functor that allows us to change between what type family we're over. And this base change functor has left and right adjoints. So if you're familiar with this locally Cartesian closed business, this is the exact same way that we do quantifiers in logic. Identity types are interpreted as path spaces. So if you're familiar, this is one of those things about model categories I didn't tell you about. But one of the axioms is that every map should split as a fibration followed by a cofibration, and one of those should be trivial. So if we take just the diagonal map and factor it as a trivial cofibration followed by a fibration, by which I mean a cofibration, which is a weak equivalence, then we get the path space x equals y. It has two projections to the endpoints, x and y. And we have this trivial cofibration taking a into, so if I have some little a, I get a equals a living in this path space. So if you like, we can describe this more concretely. This is the set of all paths in A. So it's the category of simplicial sets is Cartesian closed. Indeed, it's enriched over itself. And so we can get a simplicial complex whose are basically functions from the arrow into A. And you should think about that as being paths in A. And then we can project onto the two endpoints in order to get this projection into A times A. Okay. And in some sense, this explains path induction. So one of the other things that I didn't tell you about model categories, or I guess I did, but I didn't write it down, is if you have a trivial cofibration on the left side of a square, and you have a fibration on the right side of the square, then you can lift in the sense that you can fill in this diagonal from the bottom left to the top right in a way that makes everything in sight commute, which is great. So this is going to be called J somewhat suggestively. And why am I calling this lift J? Well, because if I have some P naught, which is a function that takes an A and spits out, well, what is P fibrated, or what is some fibration over this path space? It's exactly a type which depends on this path space. So I have a function taking an A and spitting out a P of AA reffle A is saying that this square commutes, saying that where I land in P, well, it lands in the fiber of AA reffle A, because that's what this reffle arrow sends me to. And then what does the existence of this lift tell me? Well, it tells me that if I have this function P sending A to some guy in the fiber of AA reffle A, then I have this lift J, which takes any old path, xy alpha, so alpha is a path from x to y, and spits out a path in the fiber P of xy alpha. And this term is exactly telling me the bottom triangle commutes, right? It's telling me that if I lift up and then project back down, I get back to the same place where I started. And if we look at the computation rule, this is telling me that J, if I evaluate J on AA reffle A, then I should get P naught of A. And indeed, if I look at commutativity of the top triangle, I send A to AA reffle A, and then I hit it with J, and I should, by commutativity, get P naught of A. And that's exactly what the computation rule buys me. So in some sense, path induction is telling me something about this model structure. Unfortunately, everything I just told you is like very slightly a lie. In homotopy type theory, we have on the nose equality of syntax. So if I like substitute something and then I substitute something else versus making some big substitution all at once, I literally get the same syntactic object at the end of the day. Unfortunately, in simplicial sets, our structure is only defined up to isomorphism, right? So substitution becomes a pullback in this setting. And in general, there's lots of pullbacks that you could choose. And it's well defined up to isomorphism, but it's not strictly well defined. And so we need to evilify simplicial sets in the sense that we need to choose some specific pullbacks. We need to choose some specific choices in each isomorphism class. But this is tricky because we then need to make sure that these choices all agree with each other, right? Now that we're like actually making specific choices, if I have strict equality of pullbacks, for instance, in the syntax category or in the syntax of homotopy type theory, then I should expect to have strict equality in simplicial sets. And the key to doing all of this is what's called a weakly universal fibration. And the idea behind this is an idea of Voevodsky, is to sort of make all of our choices at once. So instead of for every possible construction, making a choice and then checking after the fact that they all cohere nicely, which would be incredibly difficult to do, you're sort of smarter and you make all of your choices in building this universal fibration. And then you're able to describe all of the other choices in terms of this one choice. And so everything, it's much easier to check that things cohere nicely. So from a universal fibration U, we can turn every construction into some variant of U to itself. This is what I said. This is all described in that paper of Kopulkin and Lumsdain. And every construction is a pullback along one of these variants. And so by choosing a particular pullback in each case, we're able to get equality on the nose, which is what we need to actually make this work out. So like I said, there's this incredible explanation. I didn't understand this until I was researching for this talk, and I found this paper that explains it really, really thoroughly. And should you decide to go through with learning all of this material, here's a good exercise to keep in the back of your head. This was originally going to be an example that I did, and we would like work through it together. But I realized for time reasons, it wasn't going to work out. So I'll leave it as an exercise instead. Take some inhabitants of is contractible A, and then show that the Kahn complex associated to A genuinely is contractible. And so this exercise is on the one hand hard, but on the other hand, if you really understand this syntactic translation and you know a couple facts about simplicial sets, you can really do this. And so you're going to use the semantics of homotopy type theory, of course, and then show the geometric realization. So I have some simplicial set. Now I'm going to geometrically realize it is also contractible, provided the Kahn complex is. And here you're going to use some properties of geometric realization. And now at the end of the day, you can pat yourself on the back for successfully proving some fact about an honest topological space up to homotopy using homotopy type theory. And there you go. Thank you. That's all I have.
Great. Thank you very much, Chris. We'll do our silent applause again, or using the reactions. And we have time for questions.
Yeah.
I see Torsten has a hand raised.
Okay, well, briefly, I see there's a question in chat. I trust myself to answer this more than something which might scare me. So related to the first part, what gluing of topological spaces that are not a finite construction? Oh, I'm not sure I understand your question. What happens to a topological space that are not finite constructions? Well, you can still glue infinitely many things together, right? There's nothing stopping you. Yes, you'll have a hard time coding it up on a computer, but there's nothing stopping you in the abstract from gluing together infinitely many things. So of course there's a simplicial set representing it. And so yeah, it will be represented by some type, although it might not be a type that's easy to actually tell Agda about. Thankfully, most of the things that we're actually interested in practice admit nice finite descriptions. So the relevant thing to Google there would be like triangularizable, something to that effect. Yeah, totally. And then Danny said there's a question from
Torsten. Hello?
Okay, am I allowed to say something or?
Yeah, go.
Yeah, please.
Okay, let me see whether I can. Am I here? Yeah. Isn't there an elephant in the room here? I mean, this simplicial model isn't actually constructive, right? I mean, needs choice, and I mean, type theory to me should be effective, right? So it's.
Mm-hmm.
Can you comment on this?
Yeah, totally. Yeah, so it does require choice. Maybe that's less offensive to me than it is to other people. But yeah, I'm sure Yeah, I'm not entirely sure. I think there is a way around that problem that I remember reading about, but I don't know anything about it. Do you happen, is there something you're getting at?
Yeah, I mean, there isn't really a good solution. I mean, there are cubical sets and uniform cubical sets. I mean, actually, uniform simplicial sets also works. There is a paper by Christian Sattler and there is a paper which shows that we can do uniform simplicial sets. Gambino, yeah, Sattler and Gambino, but it doesn't work for the universe, and that's a bit of an open problem. So the thing for the universe only works for uniform cubical sets. But I think there are some people working on this. And I mean, it's not offensive, but if you want to implement it, if you want to run it, if you want to compute, like you have a natural number and you hope it should be a number, then it's a problem if it's not constructive, right?
Well,
I'm a computer scientist, by the way.
No, of course, but only the semantics, right? So if you trust that the semantics really do work, right?
No, it really is a problem. If you want to implement it, run it on a computer, yeah, then you can, if you have constructive semantics, you can compute some computation which ends up to be a natural number. You can compute it. If it's not constructive, you can't.
Well, okay, sorry, maybe I misunderstood then, because the type theory itself, I don't think requires choice, does it? It's only the semantics, like the type theory.
No, but you use the semantics if you want to run, if you want to compute something, you need the semantics, yeah. So that's a way to compute things. If you don't have a constructive semantics, then you don't have a good computational behavior of the type theory either.
Right, I understand what you're saying. Yes.
I actually don't understand, Torsten, because
all
the computation happens in the syntax.
Yeah, but but the rules for the computation you get from the semantics. If you don't have a semantics, you don't know how to compute with the univalence axiom. The univalence shouldn't be the axiom; it should be construction. So basically, the way to solve this problem, to know how to compute with univalence, this was what Thierry Cocon and his co-workers did in this famous paper, and this leads to cubical acta. Without this effective semantics, you don't know how to compute with the univalence axiom.
Well, I would still say that the semantics motivates cubical agda, but cubical agda can be written down as a purely syntactic object.
Yeah, but in the end, you reflect it into syntax. You reflect the semantics into the syntax to be able to compute, but you need the semantics to start with. There's a simplicial semantics you don't know how to compute.
Yeah.
It's interesting that people are not aware of this.
Well, I just would view it a little bit differently, but I think we agree fundamentally. But ultimately, you need a syntactic theory that's computable.
Yeah, but you will only. The point is, if you really computation, normalization, obviously it relies on semantics. It's a semantic thing, reflected into syntax. But without the semantics, you're stuck. You're stuck.
I don't think we're going to get any further on this question. Are there any other questions?
How would the open sets of a topological space reflect in the type? So when you pass to the homotopy category, which is the only thing we can talk about, you lose access to the open sets. Indeed, you lose access to the points. Which should make sense, right? Because homotopy type theory doesn't have any way of giving you access to the open sets. Nor, for that matter, do simplicial sets. So what happens there is you can talk about topological spaces up to homotopy, and so I guess my talk was slightly clickbaitier than I realized, because I guess you don't have access to open sets directly via homotopy type theory. But by taking something with open sets and then looking at its homotopy type, you can talk about that through homotopy type theory. Yeah, that's a good question, though.
Henry, would you like to ask a question?
Yeah, so mine is more philosophical. I was reading a paper that shows that Popper started from, so as I understand, open sets were an initial model for intuitionistic logic, and Popper then looked at closed sets and as a dual, and came up with falsification logic, which some argue is more the logic of science, observational, where you have to also always falsify. So it's amazing they did this in the 50s. Now, you're mapping HoTT to topology, and I would have thought that you would have ended up in the open sets because you're intuitionistic, but you seem to be saying that you're not. And so I'm wondering what the relation is here between, and perhaps it's way too far away, but.
Yeah, so I'm not familiar with this falsifiable logic at all. Obviously, there's nothing wrong with trying to come up with a logic whose semantics end up being closed sets of a topological space instead of open sets. But it's not so much that when you do this, you don't end up with open sets, as much as when you do this, you end up with topological spaces up to homotopy, right? So remember, it's like 100 slides ago, so I won't bring it up. But if you remember, when we took this quotient top of, and then we inverted all the weak equivalences. And when we invert the weak equivalences, we end up with the objects of this new category up to isomorphism don't, so for instance, have a notion of open set necessarily. So you get some new category whose objects are now slightly harder to work, or I guess the objects are the same. But yeah, we can't directly access the open sets because you now have two isomorphic things, right? In the classical category top, isomorphism is homeomorphism. And so you can recover the open subsets from the homeomorphism type of a thing. But now when you quotient by homotopy, you now have two isomorphic things. So for instance, the real lines and a point, which have very different open sets, right? And so up to homotopy, the notion of open set doesn't really work. But you can still study topological spaces directly by asking questions about their homotopy type. And this is what sort of classical algebraic topologists are doing all the time.
There's another possible answer there too, which is that you can also interpret homotopy type theory into the infinity topos of sheaves over a particular space. And then the propositions in homotopy type theory correspond to the open subsets of the space. So, and I think that more closely matches the sort of the one topo story that Henry was indirectly referring to.
Mm.
Okay, maybe this is a good time to stop here because we do have more time to chat in GatherTab. So let's thank Chris again.